Hi there, and welcome to the Air Equipment LLC YouTube channel. This is part 3 of our discussion on the basics of fans and blowers. Now let's talk about fan curves. A fan curve is a graphical representation of the performance of a fan at a particular RPM. And all fans, regardless of the size, a little small bathroom fan and a 200,000 CFM big industrial blower, they all can be demonstrated, their performance can be shown on a fan curve. If we look at the curve here, the solid black line is the fan curve. That is the CFM versus static pressure. CFM is across the horizontal axis, the airflow, and then the resistance that the fan must overcome is the static pressure on the vertical axis, measured in inches of water column. The solid purple line is the horsepower versus CFM curve, horsepower being on the far right-hand vertical axis. The dotted black line is the system curve, and the dotted purple line is what we call the surge line, or more commonly known as the do not select line. We don't want to select the fan near or to the left of that surge line. So where the intersection of the system curve and the fan curve is, that is the performance of the fan. And in this case, it's doing 2,500 CFM against a ½ inch of pressure. So fan curves always slope from upper left down to lower right. And this makes sense that you're going to get the greatest airflow when there is the least resistance. So at 0 on the vertical left axis, you're going to get the most airflow. In this case, it looks like it's well over 3,000 CFM at 0 resistance. But when you add pressure to the system, when you add pressure to what the fan has to overcome to continue its airflow, the amount of air delivered will become less and less. That's why the curve goes back. If you go to the far right, and then it slopes to the upper left. Okay, with the fan curve, like I said, it is the performance of a particular fan at a particular RPM. If it turns out that our calculated system curve was not correct, in this case we thought it was going to be 0.5 inches of pressure, but let's say, for example, it turns out to be 0.7. When the fan is installed and connected to the system and starts operating, it sees 0.7 inches of pressure. Well, in that case, the intersection of the system curve and the fan curve is going to be up higher, and it's only going to deliver 2,100 CFM of airflow. On the other hand, say we install the fan and there's less pressure than anticipated. Let's just say, for discussion's sake, it was 0.3. If we look where 0.3 intersects with the fan curve, that's up at 2,800 CFM. More air than what we planned on. Now, if the actual airflow that the fan delivers is either more or less than what we want, the way we adjust to get the right airflow is to change the RPM of the fan. If the pressure is higher than we thought, we're getting less airflow, we have to increase the speed of the impeller to get more airflow, to get to the 2,500 we're hoping for. If the pressure is only 0.3 rather than 0.5, or we're getting more air than we wanted, we have to slow the fan down. And whenever we change the RPM, what we're really doing is creating a new fan curve. It'll be parallel to the fan curve we see here, but just if it's a lower speed, it'll be brought in, coming in a little lower to the aiming down towards the left-hand lower corner. If it's a higher speed, then we're creating a new fan curve that's kind of parallel but moving upward to the upper right-hand corner. The best way to understand what's happening when we change the speed of the fan is to look at the fan laws. The fan laws are telling us what's going to happen to our 3 main variables: airflow, pressure, and horsepower, whenever we change the speed of the fan. So the fan laws say that the CFM varies directly to any change in the RPM. In other words, if we increase the RPM 10%, we're going to get a 10% increase in airflow. However, when we change the speed, when we change the RPM, the impact on the pressure is that change squared. And the big one is whenever we change the speed, the impact on the horsepower needed to drive the fan is that change cubed. Big exponential impact. A real good way to understand this is, instead of looking at the formulas, let's look at an example. All right, let's say we have a fan, it's installed and it's running. It's spinning 1,000 RPM. This is our left-hand column here, initial condition. It's spinning 1,000 RPM. It's delivering 2,000 CFM of air against 1 inch of pressure, and it needs 2 horsepower of energy to make it all happen. Now, if for whatever reason we can decrease the flow, let's say we have overnight hours or weekend conditions, reduced load, if we can slow down the flow, and if we want to reduce it 20%, then we reduce the speed 20% because RPM and CFM are directly related. So if we decrease it 20% down to 800 RPM, we will get 20% less airflow, 1,600 CFM. But the impact on the pressure that the fan has to work against is that change squared. So now instead of 1 inch of pressure, we only have to work against 0.64 inches of pressure. The real big impact is horsepower. We take our initial 2 horsepower, we apply the change cubed, and now the horsepower needed is only 1.02. It's a 49% reduction in horsepower needed when we just want 20% less air. So this little example right here, this is all you need to know about why speed control devices, VFDs, ECM motors, whatever kind of control strategy can ramp the fans up and down as needed is a tremendous energy savings. Because look what we have here. We reduce the airflow 20%. We reduce the horsepower needed 49%. And that's directly related to how much energy is required to run the fan. You know, electricity right off the power grid. So a 20% reduction in flow saves us 49% on the electric bill. So slowing down our fans whenever possible is a tremendous way to save energy. However, when we slow down the fan laws save us tons of money. When we need to speed up the fans, it's kind of painful. Let's look at example number 2. Same exact initial conditions. 1,000 RPM, delivering 2,000 CFM, 1 inch of pressure, and 2 horsepower. Now, if for whatever reason we need to get more airflow out of that fan, and let's just say we need 20% more, well, we need to increase the speed 20%. The RPM goes up 20%, and we'll get 20% more airflow. In this case, the RPM goes to 1,200, and the CFM will be 2,400. But the impact on the pressure is big. We take the change and square it, and now instead of 1 inch of pressure, the fan has to work against 1.44 inches. The big one, of course, is horsepower. We take the change, we cube it, and now that 2 horsepower needed to deliver 2,000 CFM jumps up to 3.5 horsepower. It's a 73% increase required just to get a mere 20% more airflow. Quite often, we get the call, and just as an example, I'll say, we're a brand new kitchen ventilation system was installed in a restaurant. They renovated, expanded the facility, put in new kitchen hoods and new exhaust fans, new makeup air units, and they had the grand opening. It's up and running, but they find out that during the peak cooking hours, the hood is not quite capturing all the smoke. So they decide, let's increase the CFM 20%. Hopefully that'll take care of the problem. Well, they give us a call and they say, we want the fan that you just sold us, that was just installed, we want it to deliver 20% more airflow. So what we need is a new set of pulleys. please put a new set of pulleys on order so we can speed up that RPM, and that ought to cost about 50 bucks, right? Well, we have to say, hold on a second, let's run this by the fan laws and see what really happens. So when we input the data of the existing fan, how it's running, and we apply the fan laws for that 20% desired increase in CFM, we discover that the horsepower goes up 73%. And so what we have to say to this restaurant owner is, well, hold on a minute, the fan laws are not going to let us do that, because even though you only want to increase the speed of the fan 20%, it's going to require much more horsepower, and unfortunately, the fan you installed only has a 2 horsepower motor. So you need a bigger motor. And they don't make a 3.5 horsepower motor. The next size is 5 horsepower. So it's not just $50 for a new set of pulleys to speed up the fan. You need a whole new motor, and that's going to cost about $500. So the restaurant owner says to us, "Oh, you're kidding me. You mean I got to spend $500 for a brand new motor just to get 20% more CFM?" And then we get to be just like the late night infomercials on TV, and we get to say, "But wait, there's more." You see, Mr. Restaurant Owner, the fan that was installed doesn't have a motor compartment big enough to hold a 5 horsepower motor. So you actually need to get a brand new fan, and that's going to cost about $2,000. And now he's outraged, he's livid. $2,000, but wait, there's more. The new fan requires a new curb. You got to have the builder come back and cut a bigger hole in the roof. And the new fan requires all new electrical service, because a 5 horsepower motor needs a bigger circuit breaker, needs thicker gauge wire feeding it. So between the builder and electrician, that could run another $15,000. So at this point, he doesn't know what to think, because he thought he was going to spend $50 for a new set of pulleys to speed up the fan, and now it looks like he's got to spend $15,000 just to get 400 more CFM. Well, in the real world, no building owner would ever spend that much money just to get 400 CFM. Quite often what they do is either nothing and just live with the problem of a little bit of smoke in the kitchen during peak cooking hours, or sometimes what they'll do is they can purchase not a 5 horsepower motor, but a 3 horsepower motor that will fit in the motor compartment, speed up the fan as much as possible. Instead of getting 400 CFM, maybe they'll get 250, and maybe that'll solve the problem. But when this happens, and we get a phone call like this, usually a couple times a year, when it happens, nobody's happy. The owner of the business is not happy, because he thinks, sometimes he accuses us of lying, that we're making this stuff up, and we have to say, no, it's just the fan laws, and we obey the law. That's just a fact of physics. He's not happy because he thinks it's a real simple fix to get the air he wants. We're not particularly happy because we've been on the phone for an hour with this guy, and we're getting accused of being liars, and there's really no easy solution to the problem. So the best way to avoid a situation like this is, when you're specifying fans, never pick the fan that's spinning at the highest RPM and maxing out the motor horsepower, and assuming that your design conditions are what is going to be found in the field. Always select a fan with a little room to move, maybe even a little bit more than a little room to move. And if the brake horsepower on your selection is 1.9, don't pick a 2 horsepower motor. Put a 3, maybe even a 5 in that fan, so there's plenty of horsepower if it's ever needed. Because quite often, once the fan's installed, it is determined that we need more CFM than planned. Or when the fan's installed, we thought it was going to be against 1 inch of pressure, it turns out it's 1.4. Either way, there's an exponential impact on horsepower required. So when selecting fans, always select a fan that's got some room to move, so you don't have these horrible situations like we run into far too often. So in our next segment, we're going to talk about some more exciting aspects of the basics of fans and blowers. So please stay tuned.